All right, today we're going to look at integration by substitution. So basically so far all we've done is the, basic power rule type of integration where you go up one, divide by the new power, and over. But we're going to have some other techniques to go through and do some integration. Substitution will be the most basic one of the other techniques. It's kind of like the reverse of the chain rule, or the chain rule for integration. Okay? So for integration, we have to get things in certain forms to make them work for us. So, for example, we couldn't integrate something like this. We multiplied it out first. We got it into a different form. Okay. The goal for us is these should be simple. Right? These should be very simple integrals for us. Let's go x cubed dx. Let's see, square root y dy. Something like sine theta d theta. Those should be very basic ones for us. X to the fourth over 4 plus c. Change that to a half power. So we're going to go y to the 3 halves over 3 halves, or times 2/3. Okay. And then sine theta integral will be negative cosine theta. Okay. I say easy, there's not a lot to them. Power rule, get it in the right form. Okay, we have some memorization here, but it's still pretty basic. Right? And the reason is because we're looking at a single variable. So think of this with parentheses around it. I'd have just an x. Parentheses around it with the half power, just a y. And parentheses around this would be just a theta. Something like that. We're going to use this idea to deal with some of the others. Where I run into a little bit of a problem is if I have something like this. Square root 3x plus 7 dx. I don't have a nice basic singular variable like I do here. That's what I want, is that nice basic singular variable. Because if I can write this as y to the 1/2, it just goes back to using my exponent. Okay? This is a little bit different because I have more going on in here. This is where the substitution aspect will come in. What I'm going to do is let u equal 3x plus 7. Now just visualize what will happen here. When I substitute that in, I'm going to have square root u. I know it's a different letter than y, but then it becomes this basic square root. Pretty okay with that? Mm-hmm. Right. Now I mixed up the variables over here. You've seen this before though. X, dx, y, dy, theta, d theta. And we don't see this. If it's a differential of y, it's a dy in there. That means that I cannot just substitute u in here with this here. I can't mix u's and x's. So if I have a u, that means I have a du. Du would be 3 dx. So I'm looking right here. Du, 3, 0, dx. Now it looks a little weird sometimes, that dx sitting over there. Let's think about it like this. Derivative of u with respect to x, du dx would be 3. We're used to seeing a dy dx. It doesn't matter what the variable is. Du dx is 3. Well, I can multiply the dx over, and I've got this. Everybody okay with that? Okay. Now, I'm looking back at my problem. I'm going to have an integral. I'm going to have a square root u. And then I look right here, and dx is what's left. And I need to substitute this in, but I don't have a 3 dx. I just have a 1 dx. So I'm going to bring this over. 1/3 du is dx. So I've got this piece going in for u. I've got this piece going in for that dx piece. Are you okay there? So I'm going to rewrite it like this, 1/3 dx, 1/3 du. u. Typically, we bring coefficients out in front. I'm just writing it like that to show the direct substitution for this dx on the end. So normally how I would write this problem would be 1/3 integral u to the 1/2 du. U to the 1/2 from the square root. I'm just going to bring that 1/3 up in front. It doesn't matter if you leave it on the inside or the outside. It's not going to change anything. So kind of think back to something like this. If I threw a 2 in here, it's still x to the 4th over 4. I know I'll reduce the 2. It wouldn't matter if the 2 is in here or outside. It wouldn't change anything. Okay? So now I'll continue my integration. 1/3 times 2u to the 3/2 over 3 plus c. U to the 1/2, up 1s, 3/2, divided by 3/2, the same as multiplying by 2/3. And this makes my final answer 2/9 times 3x plus 7 to the 3/2 plus c. So my answer will be in x's because that's what I started with. So all I did, made this 2/9, and then just back substituted for my u. U was the 3x plus 7. So our goal, we're going to take something that is not a singular variable. We'd rather have the singular variable. So by doing the substitution to make it one, I get a much easier integral. Or I say basic. That's what we call a basic integral. There's not much to it. Where the adjustment came in was fixing this guy over here to match this one. Let's look at something like this. Let's say integral 2 times 2x plus 5 to the 5th dx. Now, if that was a square, 2x plus 5 squared, I might just multiply it out. I can square it out pretty quick. I don't want to do a 5th. That's a lot of work, and I'm a little bit lazy. It's a lot of multiplying. But if I had just x to the 5th, something like this, it'd be a lot easier. Okay, so that's where my substitution piece is going to come in. This 2 out here isn't bothering me. That's just a coefficient. Right? I wish that was a single variable to the 5th. So there's my u piece. I'm going to let u be 2x plus 5. And just think, if you did that, you would have u to the 5th. Makes it a nice, easy integral. Okay. Now let's get rid of the dx, because if I have u, I've got to have du. Du is 2 dx. When I start the substitution, u to the 5th, and it would just be a du because here I have a 2 and a dx right here. There's 2, there's dx. That would be du. Here I had to divide the 3 over because I only had 1 dx. Now I've got 2 dx. Sometimes it looks a little different because the 2's sitting away from it. But we could rewrite this as 2x plus 5 to the 5th times 2 dx. Doesn't matter which side the 2's on. We're just used to seeing it in the front. This then makes this a pretty easy integral. Now we're back to what we'd say basic. Okay? U to the 6th over 6. Okay? Easy process there. So my integral would equal, which then my final answer would be 2x plus 5 to the 6 over 6 plus c. So I'm going to back substitute and get my x's back in there. Okay there? We're trying to make a complicated look here to an easier one. This should look a whole lot easier than that. I'm trying to get back to one of these basic forms. And this is really all we've dealt with so far, those basic forms. How about x dx over the square root x squared plus 1? The fraction in there, square root, definitely a complicated looking integral. Okay? Definitely not one of these basic ones we talk about or like to see. Okay? So my goal on a substitution, and we're going to have a lot of these different processes. Substitution's our first line of defense. If it's not easy, my next step is to think, can I substitute? Okay? So if I try to substitute here, I really only have three choices for the u. I can let u be x. I can let u be x squared plus 1. I guess I have four choices. I can let u be the square root, or I can let u be the whole fraction. U being the whole fraction is probably going to make things way worse. Okay? Think about what the du would be going through there. A lot uglier. U being x, du would be dx. Well, that's not really helping me down here at all. Changing anything. Look for the exponent. This is the exponent, the half power. That's where I'd want u to be. U would be x squared plus 1. Now I know it's in the denominator. But right now I'm trying to see what I can get work. And when you do a u substitution, sometimes it's really easy to see because you have no other choices. And sometimes it's not, and you'll try something for u, then go to du, and it's just not fitting, not working, back up, try a different u. Okay? But usually when I see an exponent, and I've got to remember, radical symbol's an exponent. That's usually going to be my clue. Now let me see if I can make it work. Du. All right, if u is x squared plus 1, what's du going to be? 2x. All right, so we'd have 2x dx. Now let's take a look at this. U is going in here. That's u to the 1/2. I can deal with that. I can bring it up, make it a negative 1/2. I'm not worried about that. Okay? Did this guy take care of the x dx? And it did because it's sitting right here. This is a 1 x dx. This is a 2. So my next step would be take half. Half du would be x dx. You can divide that coefficient over. I can fit it in. I'm going to pull the half out front. Integral u to the negative 1/2 du. So let's kind of look at what I did here. If I put in a half du up top, picture that half coming out front out of my way. Okay. This would be the square root of u on the bottom. And I just brought it up so I can work the exponent. That's where I got u to the negative 1/2. Everybody okay there? Integrate. 1/2. Let's see, this would be 2u to the 1/2. If I go up 1, I'd have a half. Divided by half is multiplied by 2. Plus c. And 2 is going to cancel. And let's see, what's u? X squared plus 1. So x squared plus 1 to the 1/2 plus c. Now, you've seen this before. I don't care if you put the square root back in or leave it a half power. It doesn't matter. You can still check this using your derivative rules. Your derivative rules, half comes down. This to negative 1/2 times 2x. 2 would cancel with the half. This went to the bottom. this one. 6 comes down, times this to the 5th. Notice the 6's we cancel. Times 2, chain roll. So you go right back to it. 3/2 comes down. That would actually make, what, 1/3 times this to the 1/2 times 3. 3 is going to cancel with the 1/3. Getting me back to that original problem. Let's look at a trig function. Trig function. I want this. Oh, basic. I want sine of something, cosine of something, secant squared of something. It's an individual variable. So let's say we had this. Let's go integral of cosine 3 theta d theta. Well, the part that screws me up is the 3 theta. I wish it was just theta, just a regular old variable. So that's going to indicate where my substitution is going to try. U would be 3 theta. That means du would be 3 d theta. Now I look at my problem. All right, this will go to cosine u. And that's what I wanted. Not a big deal there. But I don't have a 3d theta. I just have a 1d theta. Now I'm going to divide that 3 over. 1/3 du is d theta. Now I have a direct substitution for d theta. It's 1/3 du. I'll go ahead and just pull the 1/3 out front. And then I'm ready to integrate. Integral of cosine is sine. So 1/3 sine u plus c, which would be 1/3 sine 3 theta plus c if I put the substitute back for u.
Wait, isn't it?
Oh, that was it?
Integral. This is the integral. Right.
Yeah?
Oh, okay.
Integrate cosine.
Okay.
You're going to do that a lot in the beginning with the trig functions. They flip back and forth and have the wrong integral or wrong derivative because you're thinking the wrong way, the opposite way. Pretty common. Let's try a different number here. Let's go with, let's go integral 3x squared times 4x cubed plus 5 to the 7th dx. Now with that 7th power there, definitely one you don't want to multiply out. What do you think u should be? Should it be the 3, the x squared, both of these, this inside, whole thing, what?
4x cubed plus 5.
All right, let's give it a shot. U equals 4x cubed plus 5. Usually the clue is seeing this exponent. Because that's going to give you the u to the 7th. All right, let's see if we can make it fit. Du then would be 12x squared dx. Numbers, if numbers are different, these coefficients are different, they're not really bothering me. If I've got the variable piece right, I can make the numbers correct by dividing or multiplying something over. Okay. I have a 3x squared. My du gave me a 12x squared. So that means that I would need to do 1/4 du would be 3x squared dx. Now sometimes that leap going from here to here is a little tough to see. Here's one thing I would recommend. If you struggle getting some of these numbers to match up, go ahead and divide the 12 over. So you'd have 1/12 du is x squared dx. Everybody okay with that?
Yeah.
And now if I want a 3 here, can I multiply both sides by 3? And there's where I'm getting the 1/4. Do it in 2 steps. Right? Sometimes they match up really easily, in fact perfectly. Other times I can do 1 step to get it to what I want. And sometimes it's a little difficult, it's a couple steps to get there. But if you struggle with that, I would suggest doing the 2 steps. Get rid of that 12 first, and then you're back to 1. And then you'll multiply both sides by 3. And then that's where I got the 1/4, because 3/12 was 1/4. You okay with that? I mean, it only takes an extra second to do the second step. Not that big a deal. Now I'm set. 3x squared, there's my 1/4 du. U to the 7th, so here's my integral. 1/4 integral u to the 7th du. All right, now again, what we're going for here is, this should look really easy to you right now. This, not so much. Okay? But if I can get it reduced down to something like that, there's that, back to that basic integral for me. That's what I want. So let's see, we'd have 1/4 u to the 8th over 8 plus c, which would be 1/32 4x cubed plus 5 to the 8th plus c. You okay there? Okay. Different look here. Let's go 4 minus 2 cosine theta cubed times sine theta d theta. Definitely ugly looking. We get this simplified. What should we try to make u be first?
4 minus 2 cosine theta.
So we clue right into that exponent. There we go. So u would be 4 minus 2 cosine theta. So now let's go get du. Derivative of cosine is negative sine. So this would then be a positive 2 sine theta. Everybody agree with that? Okay, so does this fit perfectly? No. What's in the way? The 2. How do we get rid of it? Divide it over. Here we go. 1/2 du sine theta d theta. And now everything fits in. So let's see here. We'd have 1/2 integral u cubed du. And then that's kind of back to what I was talking about. That's a simple one here.
Yeah.
That's one of my basic ones. So I'm going to have 1/2 u to the 4th over 4 plus c. That's my integral. And so that would give me 1/8. Where's my u? There we go. 4 minus 2 cosine theta to the 4th plus c. And I don't care if you write it like that with the 1/8 in front, or you put it all to the 4th over 8. That's not going to change anything. Wouldn't matter at all. Are you okay there? Now let's make sure we're understanding the difference here. You don't need to write these down. I just want to look at a few problems here. If I give a couple different examples up here, we're just going to kind of look and say substitution or not substitution. All right. Substitution here. Is it necessary? No, because you can distribute the x, right? All right. You could use substitution, though. Because if you let u be this, du would be 6x. I can use the 1/6 and get to the x. But probably quicker to just distribute the x and then go through the integration. The game changes when we get to this point because I can't distribute the x unless I multiply this out. Now I want to go for that substitution because I don't want to do that fifth power. That's going to be more work. Now, if this was a square, maybe. I personally would probably still do substitution, but you could square that out pretty quick too. Yeah, but anything higher, I wouldn't want to. Right? I really can't do anything if I had a fractional exponent there. But I can do that use substitution. I'll get that piece. Are you okay with that? All right. Now, let's look at a definite integral real quick. On a definite integral, if I had, let's see, 7, okay, 0 to 1, x squared plus 1 cubed dx. Now, we talked about how a definite integral, you've got to know the process, but yes, your calculator will do a definite integral. So you can actually put this in your calculator, calculate it out, get the final answer. Okay, but let's look at the substitution process on a definite integral. Forget the 0 and 1. If you're just looking at this, that's tough to integrate. That's where my u is going to be at that x squared plus 1. Everybody agree with that? So we're going to have u x squared plus 1. du is 2x dx. And then what will be the next step? Get rid of the 2. Yeah, we're going to divide the 2 over. So 1/2 du is x dx. Look okay to everyone? Okay. So now when I substitute, I'm going to have integral, I guess it'd be 1/2 integral u cubed du. Does everyone agree with that? Mm-hmm. My limits now become 1 to 2. Any idea why they changed? What's that?
Is the half, the 1/2 of that side?
No, not the half. You're on the right track because we did end up with a half, but it's not the actual value of the half. Yeah.
Because we have the 2x dx. Or I guess that's the same as the half, never mind.
Let's see. What variable's over here? X. So these refer to x. What variable's over here? So I can't use x. If I have x, x limits. If I have u limits. I was like, well, where'd the 1 and 2 come from? It's easier than you think. If x is 0, what's 0 squared plus 1?
What?
Use 1.
Oh, okay.
If x is 1, 1 squared plus 1, 2. Use 2. The limits aren't really that big a deal. It just looks like they appear out of nowhere. Okay? But the variables are key. Whatever variable's in here, in this case it's x, that's what these limits refer to. So when I switch the variable to u, I can't have x limits in there. I have u's now. So if I'm going to switch the variable to u, I've got to have u limits. So 0 squared plus 1 gives me a u value of 1. 1 squared plus 1 gives me a u value of 2. Okay there? And now we integrate. 1/2 u to the 4th over 4 from 1 to 2. And so then that would be, let's see, that would be 2 to the 4th over 8 minus 1 to the 4th over 8. 15 eighths. Okay. Now notice I didn't go back to x's this time because I have u limits. I'm finding u's.
If you converted the limits back, would you be able to go back to that?
If I convert it back and go back to x, I could do this. I'll say or 1/2 integral u cubed du would be 1/2 u to the 4th over 4, which would be 1/8 x squared plus 1 to the 4th from 0 to 1. Substitute in. Let's see, that would be 2 to the 4th over 8. Does that have 1 plus 1? Minus 0 plus 1 is 1 to the 4th over 8. Back to the 15 eighths. Now notice what I did here. When I rewrote the integral with u's, I did not put any limits on. I integrated, did not put any limits on. Put the x's back in, put the limits on. I know it's kind of picky, but on that AP test, you've got to make sure things match up. So as soon as you write this, it's wrong. Because those are not the limits for you. So if I'm going to go the route and bring the x's back in, that's fine. I'm just not going to bring the limits back in until I bring the x's back in. And go back to those x limits. Most of them are pretty easy to switch. You just look at this piece right here. To switch over, then you don't have to go back. But some students, and I still do it every now and then, go back to x's. Some students really like going back to x's all the time, and that's fine. Just don't pull these limits back until you get the x's back in the problem. That's what you do. Everybody okay there? So nothing changed on the integration. Nothing changed on how you work the substitution process. Only thing that changed was we got to fit the limits, and then we were doing what we did last class, where we're actually integrating and then substituting in. That part's not new. The new piece was switching those limits, something like that. All right, let's see.